Okay, let's do number 27. And it states, consider an animal population, P of t, which is going to be our solution to our differential equation, with constant death rate, delta. So I just, again, wrote down a lot of given information. And we have the birth rate, beta, is proportional to p, which basically means beta is equal to A times the population. And let's see, other information. So P of 0 is 200. P prime of 0 is equal to 2. So there are two questions. Part A is when is P 1000? And part B is when does doomsday occur? Okay, so again, we have our differential equation, and we need to find a function P of t that models this animal population. So again, we're going to use a lot of information from the previous problems. So we know dp dt is equal to, we know beta is really AP, right? I mean, it's right here. And we know what delta is, right? Delta is 0.01 or 1/100ths. And let's see, we have our, right, we still have our differential equation. We just substituted some values. dp dt is equal to, again, we can factor out that AP as we did before in, again, in a previous problem, and I'm going to be left with 0.01 over A. And, well, let's separate our variables, right? We always want to separate our variables. And let's see, when we separate our variables, let's see, moving things around, let's see, we're going to end up with 1 over P times the quantity. So we have this guy, dP is equal to, and again, another nice A dt. So, I mean, I skipped some steps here. You guys can move things around by now, I hope so. So then we're ready to integrate. And again, this is going to be another partial fraction, partial fraction, no S, decomposition, right? In order to integrate this guy, we need to separate this this expression. And again, we're going to determine our A and our P, and it's the same process as the previous problem. So I'm going to go ahead and write the model because we really know our model already. But I did want to go through that process just because we're going to be using partial fractions quite a bit in the next section. So we're going to end up with this model, and it's going to be, so 0.01 over A times 1 over 1 minus, again, that's C, E to the, and then this is going to be my delta T. And so again, the question is, when is P 1000? And so in order to find that information, we need to know what A is, and we need to know what C is. So we have this model, but we need to know what A and C are. So we're going to use our differential equation, right, given above. Actually, well, this one specifically, or even this one. So I'm going to use this one. And so using that guy, right, let's just, again, plug in some values that we know. So I'm going to write, since dp dt is equal to AP minus 0.01 P, well, again, this is just P prime of t. And I'm going to go ahead and write my p's as function of t's, as that's what we're really finding. And again, given information, we know P prime of 0 is 2. So I'm going to use that given information. So P prime of 0, right, this guy's going to be 2. And so I have the following: a p of 0 minus 0.01, and then we have p of 0, and I end up with the following. Well, p of 0 is going to be 200, so this is really 200a, minus 0.01, and then of course this guy is still 200. So again, we get a nice linear equation. I'm just going to dot, dot, dot. You can divide both sides by 200. This is just a simple algebraic equation, but you're going to end up with 0.0001. Okay, so I found my A, and now if I substitute it back in, remember my model was so 0.01 divided by A, which I just found, and maybe let's put it in a different color just so you know, right? I'm inserting that guy, times 1 over 1 minus C, e to the delta t. Okay, so we need to find C now. So we can say we have this model. Let's see, we know, and we can actually simplify this a bit, and when we do, we actually end up with 100 over 1 minus CE, and then of course delta t. And we can use p of 0 again, because p of 0 is, this is just going to be 1 minus c, because again, if t is 0, well, this guy, right, this is really e to the 0, which is 1. And again, p of 0 is gonna, let's see, what was p of 0? I believe was 200. So 200 equals 100 over 1 minus c. Again, cross multiply, solve for c. So I have found my A and my C. So I can definitely input that into my model. And so we are left with, so we have P of t equals 100 divided by 1 minus, so a half e to the delta t. And let's see, we can, well, this is fine. If you have this model, it's not wrong. I'm just going to go ahead and multiply by 1 just to make this look a little nicer. So 200 over, right, I'm just multiplying top and bottom by 2, so I get 2 minus e to the 0.01 t. Okay, so this is our solution to our differential equation that we started with. So now that we have this model, let's go ahead and answer the questions. So part A, when is the population going to be 1,000? Well, I mean, we have the model, so let's put in 1,000, and well, when is referring to t. And again, this is just a college algebra equation that we're solving. Again, you can cross multiply, then use a natural logarithm. So let's see, dot, 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 2 minus e to the 0.01 t equals 0.02. So I'm just skipping a couple steps. I hope that's okay. It's again, this is just a college algebra equation. I don't want to bore you with the easy part, but hopefully you can, again, go from here to here. And again, solving, right, moving things around. So e to the 0.01 t. So I'm going to end up with a negative, or actually 1.8. And to solve for t, right, again, you can natural log both sides, bring down my, my 0.01 t, because that's definitely a power rule, using logarithms. And when you solve for t, right, you end up with natural log of 1.8 divided by 0.01. So again, let me maybe, right, I can take the natural log of this side, right, bring my power down, right, using the power rule of logarithms. and we end up with this value. So t is approximately 58.78. So for the population to get to 1,000, it takes 58.78. And what's our time in this case? In this case, what are we talking about? Per month, so months. Okay, part B. So when does doomsday occur? That is, when does a population explode without bound? So we have, again, I'm writing my my model. 0.01 t. And, well, doomsday is definitely going to occur when my denominator, right, because it's without bound. So it's going to explode, right? There's no horizontal asymptote. There's no limit. So it's going to occur when this expression approaches 0. So let's go ahead and maybe write that down. So doomsday occurs when, right, this guy, let's write my 0 here, when this guy approaches 0. So if we set it equal to 0, we can solve for t. Okay, so again, another college algebra equation, and oh, I think I need a new iPad. Oh, there we go. There we go. Let's move this up. Okay, so solving for t, again, just going to move things around. So we end up with 2 equals e to the 0.01 t. I can definitely take the natural log of both sides, and the reason I want to do that is because those guys are going to be, it's going to give me the identity, and I'm left with this guy. Therefore t, so it's going to be approximately natural log of 2 divided by my the delta that was given. And so if you punch that in your calculator, whoops, it is approximately 69.31, and so our units in this case, I think it was months, proportional, yes, deaths per, so per month. So it's going to take, so at 69.31 months, doomsday is going to occur, meaning our animal population is, it's going to explode. And if you graph this, right, this is it's an exponential function, right? We have an exponential function. And so if you graph this on your calculator, so I'm going to do a quick sketch here. All right, so t function p of t. So I'm just going to punch that in my calculator really quick. And so we get, right, it looks something, you can punch it in as well, right? You get something like this. And then my, right, the vertical asymptote, right, is our 69.31, so almost 70 months. So at that time, this is going to explode. The animal population is going to explode. And so that's the kind of graphical view of what's happening here. So hopefully that makes sense. Again, a lot of algebra in this. It wasn't too bad. We did use calculus, obviously, but a lot of logarithms. So that is the last problem I will do in this section. And again, you're more than welcome to ask me questions if you need clarification. Let me know. I've been definitely sending a lot of JPEGs to students who ask me questions via email, or if they're on a discussion board. Okay, that is 27.